This is just some circular motion basics that we need to know to discuss circular motion. And as you already know, we define circumference as 2 pi r, and we define the period, which in physics is usually given the symbol capital T, as I'm going to give this two definitions. We're going to say it's the time it takes to rotate once, rotate or revolve, and until you return to where you started from. A working definition would be the number of seconds per rotation. That's more of a working definition, or revolution, if you will, depending on what you want to call it. And that's the definition of period in circular connotations. Period may have other meanings in wave theory, where the period is the time it takes for a function to repeat itself. That actually is compatible, and I'll show that a little bit later on. But that's our definition of period. Let's look at a practical example of that. Let's say we have one of those old plastic records, and it's spinning at 45 RPM. That would be revolutions per minute. We want the time it takes to rotate once, or we want the number of seconds per revolution. Well, we've got the number of revolutions per minute. If I could write this as 45 revolutions per second, I'm a little bit closer to doing that. So in 1 minute, there are 60 seconds. So really, this is 45 revolutions per 60 seconds. Now, I want seconds per revolution. So therefore, I just have to flip this upside down to get seconds per revolution, which is our definition of period. That would be our capital T. Capital T is then going to equal 60 seconds divided by 45 revolutions, which, if you do the math, T then becomes 1.33, and it's a repeating seconds. And usually that is how the period is expressed. The period is expressed in units of time. In our international system of units, that would be seconds. However, the period could be hours, it could be days, it could be years. I point out that what's implied, it's 1.33 seconds. What's implied is per revolution, but usually never expressed explicitly like that. Let's try another one. How about something that is traveling 20,000 RPM, revolutions per minute, and we want to find the period? Well, then this is going to be equal to 20,000 revolutions occurring in 60 seconds, and then we want to invert that so that we get there are 60 seconds in 20,000 revolutions, and that turns out to come out to be just 0.003 seconds per revolution. And so that is our value for the period. And that is equivalent to 3 milliseconds. If you will stretch. So in 3,000ths of a second, this thing will go around once. We can extend this to other objects, like, for instance, the moon traveling around the earth traveling around the sun, and things like that. But we'll look at that in a moment. That's our definition of period. Well, For an object traveling in a circle, an object traveling around in a circle like that, we can see that the distance it covers is given by, as we just said before, the circumference, 2 pi r. The time, what is the time it takes to go that distance? Well, we just defined that time as the period, capital T. Therefore, we can write for our velocity. What is the velocity of the object? Therefore, the velocity is just going to be defined as distance over time, or v is going to equal 2 pi r, the circumference, divided by the period. And this is one of the key equations of circular motion. The velocity equals the circumference divided by the period. And we'll see how that works. Let's look at an application of that. Let's find the velocity of the moon. Now, this, I should mention, is actually called the tangential velocity. It's the velocity of an object spinning around that if you were to let it go, it would fly off in a straight line like that. So that's the tangent velocity. You spin it around like a slingshot and you let it go and it goes off in that velocity. That's the v equals 2 pi r over t. So I want to find the velocity of the moon. Well, the radius of the moon is going to equal, 200 and roughly the average radius. It's 239,000 miles. It's not a circle. It's not a perfect circle. It's elliptical. It goes from 220 something to about 240 something. So on average, it'll be 239,000 miles. It's the mean distance of the moon from the Earth. So that's our R. I'm going to do this in miles per hour instead of meters per second. It'll make it a little more understandable. What's the period of the moon? How long does it take the moon to orbit the Earth once? Well, it's roughly a month, a little less. It takes 27.3 days for the moon to orbit the Earth. Now, notice that's days. Well, we want to do this in miles per hour. So what we have to do is convert that to miles, hours. And so there are 24 hours per day. And so that's going to equal 27.3 times 24, 655.2 hours. All right, so now we just have to apply our equation. We have v equals 2 pi r divided by the period, 2 pi times 239,000 miles, all divided by 655.2 hours. And we are going to end up in miles per hour. So let's see, that's 2 times pi times 239,000, all divided by 655.2. And we end up with 2,290 miles per hour for the velocity of the moon orbiting the Earth. Which sounds fast, but it actually isn't fast for an astronomical object. The Earth is actually moving much faster, something close to 70,000 miles an hour as it orbits the sun. That's another calculation we'll do some other time.